Yes friends, welcome once again to the class, and today we are going to learn the concept of half-life and why it is used. Okay, so this is lecture number 40 of physics optional UPSC nuclear and particle physics part. The chapter name is nuclear and particle physics, and this is lecture number 40 of nuclear and particle physics. Okay, so we are going to learn this particular concept, that why is the concept of half-life used. Okay, before learning about metastable states, it is very important to learn the concept of half-life. Okay, and why is the concept of half-life even used. Okay, that fact we are going to learn. Okay, so suppose we have initially this particular thing, that this is your higher nuclear state and this is your, just a second guys, just a second. Okay, so this is suppose your higher nuclear state and this is suppose your lower nuclear state. And you already know that according to nuclear shell model, what is the thing which we have with us? According to nuclear shell model, we have various energy levels in which the nucleons reside. We have various energy levels in the nuclear shell. Okay, in the nucleus, inside the nucleus, we have various energy levels where the nucleons reside. Okay, we have various energy levels where the nucleons reside. And the place where these nucleons reside inside the nucleus, that particular place, each of those places is called as a subshell. Okay, now all these subshells, what is the thing which we have in subshells? In subshells we have nucleons filled up, just like electrons are filled up in the atomic shells. Electrons are filled up, right? In the atomic shells, electrons are filled up. Similarly, in nuclear shells, nucleons are filled up. Now this is suppose your particular lower nuclear state. Okay, which we have with us. This is your lower nuclear state which we have with us, and this red dot is a nucleon. Okay, this red dot which has been shown over here, it is what? It is a nucleon, and this particular line shows the lower nuclear state, suppose. Okay, and suppose we have higher nuclear state, and this is suppose like this. Okay, now what happens is that this particular nucleon which resides over here, it suppose jumps. Okay, this particular nucleon jumps and goes over here. After jumping, it goes over there, and in that particular thing, as the red dot is what? It is nucleon, right? This red dot is nucleon, so it jumps, suppose. So after it jumps to the higher nuclear state from the lower nuclear state, what happens? This particular state will be called as the excited state, right? When the nucleon will reach over here, it is called as, this particular process is called as excitation process, right? This particular process is called as excitation process, and the nucleon will excite. Okay, this is what? This is the ground state, and this is what? This is the excited state. So we can write over here, clearly write over here that this is what? This is ground state. We can clearly write this thing over here, and this is what? This is excited state. We can clearly write this thing over here. Okay, now let us move on to the next slide. The situation on the previous slide exists in, suppose, 10 to the power 23 nuclei. Okay, so this particular situation, this particular screenshot, okay, we have suppose 10 to the power 23 nuclei with us. Okay, because whenever we will have some material with us, so that material will have a huge number of atoms, and that huge number of atoms will contain huge number of nuclei, right? Those huge number of atoms will contain huge number of nuclei. Each atom will have one nucleus. Okay, each atom will have one nucleus. So if we have 10 to the power 23 atoms, then we will have 10 to the power 23 nuclei. Okay, and inside those 10 to the power 23 nuclei, each of the nucleus out of those 10 to the power 23 nuclei, each of the nucleus is passing through this condition. Okay, each of the 10 to the power 23 nucleus has this particular condition, that the nucleon has been excited from this ground state to this particular excited state. Okay, and the nucleon has now reached over here. The nucleon has now reached over here in this particular excited state. Okay, so the nucleon has reached over here. Okay, so this is the situation which we have with us, suppose. Okay, so the situation on previous slide exists in, suppose, 10 to the power 23 nuclei. So the situation which has been shown on the previous slide, that this nucleon from this lower state to the excited state, it has jumped. Okay, so from the ground state, the nucleon has jumped to the excited state. This particular situation has happened. It has happened in 10 to the power 23 nucleus. Okay, 10 to the power 23 nucleus, this particular condition has arose. Okay, this particular situation has arose. Now the concept of half-life is used because after the nucleon goes to the excited state, okay, after the nucleon goes to the excited state, not all of them return to the ground state at the same time simultaneously. Now why is the concept of half-life even used? Let us understand that particular thing. See, after the nucleon goes from here to here, okay, after the nucleon goes from here to here, what happens? The thing which happens is that after the nucleon goes from here to here, the thing which happens with us is that the nucleon will remain for some time over here. Okay, the nucleon will remain in the excited state for some particular amount of time, and after that particular amount of time, it will once again jump to the ground state. Please note this particular fact. That there are no intermediate levels of energy present in this. Okay, there are no intermediate levels of energy present in this. Okay, so this particular region which we have with us, okay, this particular entire region which we have between the two energy levels, this particular region is the forbidden region. Okay, this is the forbidden region, means no nucleon can reside in this particular in between region. Okay, this is your forbidden region. Okay, means no nucleon can reside in this particular region because it is forbidden region. Okay, so the nucleon will either reside over here, then it will directly jump to this particular state. Now according to quantum physics, you already know this very well. According to quantum physics, what do you know? According to quantum physics, you know this very well, that it is possible for a nucleon to directly jump from one particular state to another state. According to quantum physics, you already know this very well. According to quantum physics or quantum mechanics, you already know this very well, that the nucleon will jump directly from here to here. And in quantum mechanics, it is possible that a nucleon directly jumps from here to here without going in between. Okay, the nucleon will directly jump from here till here without passing through any of the area in between. It is possible in quantum mechanics. But in real life means in day-to-day life, not real life, I mean day-to-day life. In day-to-day life, when we throw a ball, okay, in real life, when we throw a ball from here to here, what happens? When we throw a ball from here to here in everyday life, it will pass through all these energy levels. Okay, it will pass through all these intermediate energy levels. Okay, because this is not a forbidden region for a ball. Ball is a macro object. Ball is what? Ball is a macro object. As ball is a macro object, so it will not pass. It will actually pass through all these intermediate energy levels. Okay, it will not jump. It cannot jump from here to here directly. If had it been a ball, had this particular red dot been a ball instead of nucleon, then that particular ball cannot go here directly from here to directly here. Okay, it cannot go directly there. It will actually pass through this particular area and then it will reach here, had it been a macroscopic ball. Okay, but macroscopic ball does not actually follow quantum mechanics. Okay, because it is Newtonian, it will follow Newtonian mechanics. Okay, actually a macroscopic ball will follow Newtonian mechanics as well as quantum mechanics. Okay, but as quantum calculations are very tedious, and those tedious calculations, there is no need to do those quantum tedious calculations for a macroscopic object. So as ball is a macroscopic object, so Newton's theorems, Newton's axioms, Newton's laws of motions work well for a ball. Okay, Newton's laws of motion work well with a ball, which is a macroscopic object. So as ball is a macroscopic object and the Newton's laws of motion hold very good with that macroscopic object, so what is the thing? So obviously we will not apply quantum mechanics to a ball and unnecessarily waste our time. Okay, because Newton's calculations are very easy as far as a ball macroscopic object is concerned. But as this nucleon will be either a proton or a neutron, what does it mean by nucleon? Nucleon means either a proton or a neutron. This particular nucleon will jump directly from here to here. Okay, it will not pass through these all states in between, because this is what? This is forbidden region. Okay, so if you click the photo of the nucleon at this particular moment, the next moment you will find it over here directly. Okay, you will find the nucleon which resides over here, which was there in lower nuclear state. This particular nucleon which was there in lower nuclear state, you will find it directly to be in the higher nuclear state. Directly you will find it in the higher nuclear state. All these intermediate regions, okay, all these intermediate region, it will not even pass through these intermediate regions. Okay, it will directly go from here to here. Okay, without even passing through this particular region. Okay, but a macroscopic ball can never go from here to here directly. Okay, it will pass through this macroscopic object will pass through all this particular region, and then only it can reach over here, because it is macroscopic object. But as nucleon, or that is proton or neutron, that is nucleon, it is a microscopic object and it is a quantum object, so it will directly go from here to here without even passing through this forbidden region. And this is forbidden region, that is nucleon cannot even go over there. So this is called as a quantum jump. This is what? This is a quantum jump. Okay, so the nucleon has gone from ground state to the excited state directly without even passing through this particular region. Okay, it has directly gone from here to here. So at 1 second it was here, suppose at time 1 second it was suppose here. So at 1.1 second it will be suddenly seen over here. Okay, so there will be no time gap, it will be directly seen. After it was seen here, it will be spontaneously seen over here. This is just an example, it will be directly seen over here. Okay, within a fraction of second, from here it will be directly seen over here within a fraction of second. So that is the meaning of this. Okay, so that is the meaning of this. So it will go from lower nuclear state to higher nuclear state, that is from ground state to the excited state. So suppose this particular thing happens in 10 to the power 23 nuclei which we have with us. Okay, this particular situation arises with 10 to the power 23 nuclei which we have with us. Now the concept of half-life is used because after the nucleon goes to the excited state, not all of them return to the ground state at the same time simultaneously. So after the nucleon goes from here to here, it will not directly, all of them will not directly return to the ground state. Okay, all of them will not directly return to the ground state. Now suppose we have this particular situation with us, that the nucleons are trying to come to the ground state once again. The 10 to the power 23 nucleons are trying to once again come back to the ground state. So what will happen? Actually, when they try to come back to the ground state, all of them will not come back simultaneously. Okay, It will not happen that all of them, like a marching soldiers army, okay, like a marching soldiers army or something like that, all of them simultaneously come back to the ground state. It will not happen. Okay, those who have been excited, they will some of them might return simultaneously back to the ground state. Some of them might return zero point 0.1 second after excitation. Some of them might return 0.2 second after excitation. So all of them will return to the ground state after some, means different times. Okay, so all of them will not behave identically. All of them, all of the nucleons which have been excited to the excited state, all of the nucleons which have been excited from the ground state to the excited state, all of them will not return instantaneously and simultaneously. Okay, all of them will not return to the ground state instantaneously and simultaneously. Okay, so some of them might return simultaneously, some of them might return after a fraction of second, some of them might return after 5 seconds, some of them might return after 10 seconds. So all of them will behave very differently. All of them will behave very differently. Okay, so the concept of half-life is used because after the nucleon goes to the excited state, not all of them return to the ground state at the same time simultaneously. So they will not return to the ground state simultaneously. Now, okay, had all the, okay, suppose if this would have been the situation, suppose, let us take a hypothetical situation that all of the 10 to the power 23 excited nucleons return to the ground state at the same time. Had all the 10 to the power 23 excited nucleons return to the ground state at the same time, what does it mean? Had all the 10 to the power 23 excited nucleons return to the ground state at the same time, what does it mean? So I will tell the meaning of it in Hindi also. Okay, so I will tell the meaning of this particular statement in Hindi now. अगर 10 to the power 23 एक्साइटेड न्यूक्लियन एक साथ ग्राउंड स्टेट पे आ जाते तो एक साथ, ओके, उस एक ही टाइम पे एक साथ ग्राउंड स्टेट पे आ जाते तो क्या होता वो बताने जा रहा हूँ मैं, ठीक है ना. So I am going to tell you that had all the 10 to the power 23 excited nucleons return to the ground state at the same time simultaneously, so then there would have been no need of the concept of half-life. Okay, then in that case we would not need concept of half-life. Had all of them come to the ground state at the same time simultaneously like army drill, okay, then there would have been no need of concept of half-life. Okay, then we would have talked about the concept of time of de-excitation only. Okay, so there would have been no need of concept of half-life in that particular case had all the 10 to the power 23 excited nucleons behaved identically and returned to the ground state in the same amount of time. Okay, had all the 10 to the power 23 excited nucleons returned to the ground state simultaneously and behaved identically, and same amount of time would have been required to return to ground state, then in that case there would have been no need of concept of half-life in that case. Okay, we would have used the term time of de-excitation simply. In that case what would we have done? In that case what would we have done? In that case we would have used the term time of de-excitation simply. In that case what would we have done? We would have simply used the term time of de-excitation in that particular case. Okay, so all the 10 to the power 23 nucleons returned identically in 0.5 seconds suppose. So all of them returned to the ground state simultaneously in 0.5 seconds. So the time of de-excitation was 0.5 seconds. We would have called it like this. Okay, we would have called it like this, that the time of de-excitation of this excited state was 0.5 seconds. That is, in 0.5 seconds all of them return to the ground state immediately, simultaneously, identically. Okay, so 0.5 second means sharply 0.5 second. They return to the ground state after 0.5 seconds sharply. So that would have been what time of de-excitation concept would have been used then. Okay, so we would have used the term time of de-excitation simply in that particular case. As each of the 10 to the power 23 nucleons behave differently, okay, as each of the 10 to the power 23 nucleons behave, now it is not behaves, behave. Okay, sorry for the grammar error, now it is correct. As each of the 10 to the power 23 nucleons behave differently, okay, so there are 10 to the power 23 such nucleons, right, which go from here to here and then from here they return to here. So there are 10 to the power 23 such nucleons. Okay, so this particular nucleon, there is only one nucleon which we are talking about. So in each of the atoms, we have 10 to the power 23 atoms. First of all we have 10 to the power 23 atoms. In those 10 to the power 23 atoms, we have 20 to the power 23 nucleus. Okay, we have 10 to the power 23 atoms. Then in those 10 to the power 23 atoms, we have 10 to the power 23 nucleus, because each of the atom will have one nucleus. Okay, so each of the atom has one nucleus. So 10 to the power 23 atoms will have 10 to the power 23 nucleus, and in those 10 to the power 23 nucleus, one nucleon is being considered which was excited. In those 10 to the power 23 nucleus, one nucleon was there which was excited. So in total there are 10 to the power 23 nucleons which were excited in total. If we take the whole bulk matter, if we talk about the whole bulk matter, then in that whole bulk matter, what happens? In that whole bulk matter, 10 to the power 23 nucleons were excited, and those 10 to the power 23 nucleons are returning to the ground state. Okay, but at different times, not identically and simultaneously and instantaneously. Okay, so it is not happening like that. It is not happening simultaneously. As each of the 10 to the power 23 nucleons behave differently, so following situation arises. So each of the 10 to the power 23 nucleons behave differently after being excited to the excited state. So as they are behaving differently, so the following situation arises. So the concept of time of de-excitation is useless. The concept of time of de-excitation is simply useless. Why is this concept rejected? Because all of them are not returning at the same time. Okay, there is no sharp time of return. Time of return of each of the nucleons. Each of the nucleons is behaving in different nuclei. The single nucleon which is excited, it is returning to the ground state at different times. So the concept of time of de-excitation, we cannot use. Okay, it would have been useful when this time of de-excitation concept would have been useful. The time of de-excitation concept would have been useful if all the 10 to the power 23 nucleons would have behaved the same way. All the 10 to the power 23 nucleons in 10 to the power 23 nucleus, if they would have behaved the same way, then time of de-excitation concept would have been used. If all of them would have returned to the ground state at the same time sharply, okay, without difference in time, that time of de-excitation concept would have been used. But as the 10 to the power 23 nucleons are behaving differently, each of them is behaving differently, so time of de-excitation concept is simply of no use. That's why I have cut it down. Okay, so each of the 10 to the power 23 nucleons behave differently. So the following situation arises then. Each of them behave differently, so following situation arises. What is the situation which arises with us? The following situation arises. Okay, nucleon number 1 returns to the ground state in 0.1 second. Okay, this is just an hypothetical example. Okay, I am just telling you what happens actually, but with the help of a hypothetical example I am telling you. Okay, so suppose nucleon number 1 returns to the ground state in 0.1 second. Okay, now nucleon number 2 returns to the ground state in 0.8 second. Nucleon number 3 returns to the ground state in 0.75 second. Nucleon number 4 returns to the ground state in 0.698 second. Similarly, nucleon number 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and the list goes on. Then we have nucleon number 10 lakh. Okay, nucleon number 10 lakh will return to the ground state suppose in 0.426 second. Okay, so nucleon number 10 lakh, when we reach over there, it returns to the ground state in 0.426 seconds suppose. Okay, then similarly the 10 lakhs become 1 crore, 1 crore become 1 billion, then 1 billion becomes 1 trillion. Okay, then 1 trillion becomes 1 quadrillion. So the list goes on, and after that the nucleon number 10 to the power 21, okay, nucleon number 10 to the power 21 suppose returns to the ground state in 0.326 second. Okay, so 10 to the power 21th nucleon 10 to the power 21th nucleon returns to the ground state in 0.326 seconds. Then 10 to the power 21 plus 1th nucleon, 10 to the power 21 plus second nucleon, then comes the number 10 to the power 22th nucleon. Okay, then comes the last nucleon. The last nucleon is 10 to the power 23rd nucleon. The last nucleon is 10 to the power 23rd nucleon. 10 to the power 23rd nucleon. This last nucleon returns to the ground state in suppose 0.999 second. Okay, so this 10 to the power 23rd nucleon returns to the ground state in 0.999 second. So each of the 10 to the power 23 nucleons, okay, so 10 to the power 23 nucleons are having 10 to the power 23 different behaviors. Okay, 10 to the power 23 nucleons are having 10 to the power 23 different behaviors. Nucleon number 1 has different behavior, nucleon number 2 has different behavior, number 3 has different behavior, number 4 has different behavior, number 5 will have different, 6 will have different, 10 lakh will have different. Okay, then 1 crore will have different, 10 crore, then 1 trillion, then 10 to the power 21 it will have different behavior. Then nucleon number 10 to the power 23 will have different behavior. Okay, so the list goes on like this. So as we cannot study all the 10 to the power 23 excited states one by one, okay, so the time of excitation and return to the ground state, so the time of returning from the excited state to the ground state, okay, the time of return from the excited state to the ground state is different. Okay, time of return from excited state to the ground state is different for all the 10 to the power 23 nucleons. Okay, the time of return from the excited state to the ground state, that particular time of return is different for different for all the 10 to the power 23 nucleons. Okay, so as we cannot study all the 10 to the power 23 excited states one by one, so obviously it is a very tedious task. To study all the 10 to the power 23 cases. All the 10 to the power 23 cases, if we study one by one, we will end up losing our life. Okay, we cannot study 10 to the power 23 different cases one by one individually. So we simply use the concept of half-life. Okay, so as we cannot study such a enormous number one by one, so we simply use the concept of half-life. Which tells us the following. Okay, which tells us the following: the time after which out of the 10 to the power 23 excited state nucleons, the time after which out of the 10 to the power 23 excited state nucleons, half of them return to the ground state. Okay, that is the concentration of excited state reduces to half. Okay, the number of nucleons in excited state reduces to half. Okay, half of them return to the ground state and half of them remain in the excited state. Okay, so half of them return to the ground state and half of them remain at the excited state. At that particular situation, when that situation arises after some time, that particular time is called as half-life. Okay, so the time after which out of the 10 to the power 23 excited state nucleons, half of them return to ground state. Okay, half of them return to ground state, thus reducing the excited state nucleons number to half. Half of them return to the ground state and reduce the number of nucleons in excited state is reduced to half, and the number of nucleons in ground state is increased by half. Okay, so the initially what will happen? Initially at time t equal to 0, all of the nucleons will be in excited state. At time t equal to 0. Okay, suppose the half-life is 0.5 second. So what will happen after 0.5 second? After 0.5 second, the number of nucleons in excited state will reduce to half, and the number of nucleons in ground state will increase from 0 to 1 by 2 into 10 to the power 23. Okay, so half of them return to the ground state, thus reducing the excited state nucleons number to half. Okay, that is 1 by 2, that is, this is the thing, 10 to the power 23 by 2 will be the case. 1 into 10 to the power 23 by 2 equal to 1 by 2 into 10 to the power 23 equal to 0.5 into 10 to the power 23 equal to 5 into 10 to the power 22. Okay, so this will be called as half life. Now let us understand what will happen. What will happen? Let us understand. So suppose we have this particular thing at time t equal to 0. This particular nucleon was over here, okay, and this was the time t equal to 0. Okay, same situation in 10 to the power 23 nuclei. Okay, so this particular photo is identical in all the 10 to the power 23 nuclei initially at time t equal to 0. Now suppose the half life is 0.5. okay, suppose the half life of this particular case is 0.5 second. So what will happen after 0.5 second? So after 0.5 second, two situations will arise. Okay, after time 0.5 second, two situations will arise. Which will be the two situations? Let us understand. What will be those two situations? Let us understand. Okay, let us understand what will be those two situations. So 1 by 2 into 10 to the power 23 will be like this, and 1 by 2 into 10 to the power 23 will be like this. So let us see. So at time t equal to 0, this particular situation was there in 10 to the power 23 nuclei. Now after half life and means t half, after half life means t half, after t half, that is 0.5 second, what will happen? This particular nucleon which was there in the excited state, it will return to the ground state in 1 by 2 into 10 to the power 23 nucleons. Okay, so in 1 by 2 into 10 to the power 23 nucleons, the nucleon will return to the ground state, and in 1 by 2 into 10 to the power 23 nucleons, it will remain in the excited state. That is, the excited state concentration was reduced by half. Okay, initially the excited state concentration was 10 to the power 23. Now the excited state concentration has reduced to half, and initially at time t equal to 0, this particular thing had 0 nucleons. This particular thing, ground state, had 0. Okay, so from 0 at t half from 0 to half into 10 to the power 23, the ground state concentration has increased from 0 to 1 by 2 into 10 to the power 23 in 0.5 seconds. Okay, so this is the situation. Okay, this particular thing has increased from 0 to half into 10 to the power 23, and this particular thing has reduced from 10 to the power 23 to 1 by 2 into 10 to the power 23. Okay, so this is the thing. So that is the meaning of half life. Okay, so the time after which out of the 10 to the power 23 excited state nucleons, half of them return to the ground state, thus reducing the excited state nucleons number to half. Okay, that is 5 into 10 to the power 22 will be called as half life. Okay, this time is fixed for a particular case. Okay, this time it depends on material to material. Okay, it depends on the nature of ground state and excited state. It depends on material to material. Okay, so this time, that is half life, is fixed for a particular material and for a particular case. Okay, for a particular case of two excited state and ground state cases. So for a particular situation, okay, for a particular fixed situation, this half life is fixed. Okay, if we take 10 to the power 24 such states instead of 10 to the power 23, okay, if we take 10 to the power 24 such states instead of 10 to the power 23, then also the half life will remain the same. Okay, then also the half life will remain the same, as it is a bulk property. It is a bulk property. Okay, so the same situation, instead of 10 to the power 23 we are taking 10 to the power 24. Instead of 10 to the power 23, suppose we take 10 to the power 24 such nucleus and 10 to the power 24 such nucleons. Instead of 10 to the power 23 this particular case, we take 10 to the power 24. The dicto case, the same case we are taking for 10 to the power 24 cases, suppose 10 to the power 24 nucleons suppose. Then what will happen? Will the half life change? Will the half life change in that case? No, the half life will not change in that case. The half life will not change in that case. Okay. So if we take 10 to the power 24 such cases instead of 10 to the power 23, then also the half life will remain the same, as it is a bulk property. As it is a bulk property, so half life will remain the same. However, if someone takes hardly 100 or 50 or 10 such excited states, okay. However, instead of taking in bulk, instead of taking in enormous number, huge number, instead of taking in enormous number, huge number, instead of taking in bulk, if someone takes hardly 100 or 50 or 10 such states, okay. So if someone takes hardly 100 or 50 or 10 such excited states, then what will happen? If someone takes hardly 100 or 50 or 10 such excited states, then half life might differ. Okay, then in that case half life might differ, because it is no longer a bulk property in that case, right? You have already learnt in the nano physics in your graduation. In graduation you have learnt in nano physics that the bulk properties are different and properties at nano scale are different. Bulk properties are different and properties at nano scale are different. You have learnt in nano physics. Okay. So instead of taking such huge numbers, like 10 to the power 23, 10 to the power 22, 10 to the power 8, 10 to the power 6, okay, 10 to the power 14, 10 to the power 16, instead of taking such huge numbers, if someone takes very small numbers, okay, like 100 or 50 or 10 such excited states, okay, so such states are suppose taken only 50 such states are taken instead of 10 to the power 23. Instead of 10 to the power 23 states, only 50 states have been taken now, or only 10 states have been taken now, or only 2 states have been taken, or only 60 states have been taken, such small numbers, or only 100 states have been taken, or only 500 states have been taken. Then what will happen? Then will the half life remain the same in that case? For such small numbers like 2, 10, 60, 50, 100, 500, for such small numbers, will the half life remain the same? Will the half life remain the same for such small numbers? The answer is no. For such small numbers, the half life will not remain the same. It will not remain 0.5 second. It will not remain 0.5 second for such small numbers, 100 states, 50 states, 10 states, okay. Then half life might differ, because then it is no longer a bulk property. Then what happens? Then it becomes a nano property. So it will not be a bulk property in that case. Then half life will not be 0.5 seconds. It will differ then. It will not be 0.5 second then. It will then differ. Okay. Because then it is no longer a bulk property. Then what happens? It is no longer a bulk property then. If we take such a small numbers 150, then it is no longer a bulk property. So the half life will differ in that case. It will not be 0.5 second. It will not be then 0.5 second. But if we take such huge numbers, 10 to the power 23, 10 to the power 22, 10 to the power 8, 10 to the power 6, 10 to the power 14, 10 to the power 16, if we take such huge numbers, then the half life in that, keeping other situations as it is, keeping other circumstances, keeping other conditions as it is, only changing the number. Okay, so in that case, this particular number, 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 and this particular number, as all of them are very big numbers and bulk property will come into existence, so all of them will have the half life as 0.5 second only. Okay, keeping the other situations as it is, keeping the other situations like temperature, pressure, etc., other things as it is. So in that case, the half-life will be 0.5 seconds only for all these things. Okay, but if you go to the micro level, that is 5 such excited state, 10 such excited state, 50, 14 such excited state, 20 such excited state, 23 such excited states, 24 such excited states, 10 such excited states, then the half-life will no longer be a bulk property, and in that case the half-life will not come 0.5 second, it will come some other number. Okay, it might be 10 years also, then it might be 2 years also, then okay, it might be 1 minute also, then so it will be different, then it will be no longer a bulk property. Okay, it will be a micro property, then it will be a micro property then. So that is the situation which we have with us. So hopefully you got the concept of half-life, hopefully you got the concept of half-life, and this concept of half-life was taught to you, this concept of half-life was taught to you because this concept of half-life was taught to you because we needed this half-life concept while studying metastable states. Okay, when we study the metastable states in nuclear isomers, then we will require this particular situation, then we will require this particular concept of half-life in studying the metastable states. We will require the concept of half-life in that case. So as we will require the concept of half-life in that case, just a second guys, just a second. Okay, just a second. Just a second.